Okay, so to quickly recap the last few lectures. Okay, so starting in Minkowski space, in our discussion of Unruh radiation, we showed that the density matrix in half of Minkowski space is thermal. Rho A is thermal, but with respect to this funny definition of energy, which is the boost charge that generates boosts that look like this. And the way we derived that was by doing a Euclidean path integral. This is a Lorentzian picture, but we thought of that Euclidean path integral as sticking out of the board, preparing a state on, at time 0. And that state was a thermal field double state, entangling left and right. And when we traced out the left, we got the thermal state on the right. Last time, we did the same thing for the eternal Schwarzschild black hole. So that's this picture. Okay, and it's just the same logic. So what we showed was that the reduced density matrix in the outside of the black hole, region A here, in the Hartle-Hawking state is thermal. It has now inverse temperature 8 pi m, which just came from the coordinate transformations. The big difference here to remember is that in this case, it was thermal with respect to the ordinary energy. Okay, in Rindler, it was thermal with respect to the boost charge. In Schwarzschild, it's thermal with respect to the energy, which is conjugate to the ordinary time variable. In other words, it's thermal according to an ordinary observer who sits out near infinity at fixed r. And our argument for that was basically the same argument. We took this slice of the black hole, we extended that out of the board some way. We extended that out of the board to define the Euclidean geometry. We did a path integral on the Euclidean geometry, found the thermal field double on regions B and A, and again trace out B and find thermal on A. And we described this state as having a bunch of entangled stuff. It's sort of entangled in pairs like this, roughly speaking, and is mostly near the horizon because it's the stuff that's near the horizon, strongly redshifted, that's able to be, that's highly populated in this thermal ensemble. Okay. Questions? Yeah.
This might be backing up a little bit, but for the Rindler picture, did we ever say why an inertial observer in region A doesn't see it thermal, like, even if they agree that that's the density matrix?
Well, I don't think we have to calculate anything to explain that fact. I mean, the inertial observer here, so our starting point, remember, was that we were in the Minkowski vacuum. Okay, so we might as well just do the calculation in the Minkowski vacuum, and then we know that this observer doesn't see anything.
Like, do you make it agree with the fact that rho A is that e to the negative 2 pi k?
Yeah, that's tricky. I think if you really have to ask an experimental question to make that a concrete question. So for example, you can ask, like, if you have a uniformly accelerating observer in Rindler, then they're going to detect radiation. So like if they're holding a thermometer that starts out at 0, the thermometer is going to go up. And when the inertial observer looks at that accelerating observer's thermometer, they're of course going to agree that it's going up, and they have to have an explanation for that. The explanation is funny. So the explanation, I think this might be discussed in some of the notes that I linked to, but I don't remember. So when this accelerating observer thinks that they absorbed a quanta from the field, a particle from the field here, the inertial observer thinks they radiated into the field. Now, oddly, they both agree that the temperature of the thermometer went up when that happened. That's a bit of a puzzle, but actually makes sense if you go through it. it turns out that well, there's a weird fact that has nothing to do with under-radiation or black holes, which is that if you detect a particle, if you absorb a particle in a thermal state, the expected energy of the thermal state of the bath actually goes up in that process, which sounds weird at first, but it's because you're post-conditioning on the absorption of you're conditioning on the fact that you absorbed a particle, and that sort of reweights the thermal distribution in a way that prefers more occupied states. So it all makes sense, it all works. Okay, so our next step, remember the strategy that I described was we were going to define a state by a Euclidean path integral on the eternal black hole, which is what we did. That's the Hartle-Hawking state. We defined that state, but we have not yet talked about what you actually see in a real black hole, and that's what we're going to do next, unless there's any more questions about this before we get going. Yeah.
So we have been saying that the modes are redshifted as they travel from this horizon to infinity, right?
Yeah.
But like we have not considered the absorption by the intervening geometry. But because like, is it true that the observer at infinity would observe a blackbody spectrum?
No, it's not. It's not. Let me come back to that when we talk about real black holes.
Oh.
Yeah. I mean, yeah. Okay. The modes are occupied with the thermal spectrum. That's not quite the same as saying that the person at infinity will see the black body spectrum. And the difference between those is an absorption factor that I'll write down in a minute. Okay, so now we're going to talk about black holes formed by collapse. So the classical Penrose diagram, by classical Penrose diagram, I mean we're not yet incorporating the quantum effects into this picture. This is the classical Penrose diagram. If you just find the classical geometry of a collapsing black hole, looks something like this. Okay, so if you look at the bottom half of the diagram, that looks like the bottom half. Remember the Minkowski-Penrose diagram? It's just a triangle. Okay, so if you look at the bottom half, you start in Minkowski space. Sorry, I didn't draw the classical one. I don't know what I was doing. This was the quantum one. There it is. So you start out in Minkowski, then you form a black hole, so there's an event horizon here. And if we just look at the upper half, it looks like the right half of the one on the blackboard, the eternal one. Note that there is no past singularity, and there is no left side of the Penrose diagram. I guess I should also draw the star. Okay, so if you have a star, the star lives on a time-like world line. So the surface of the star will do something like this, and this is the star. So if you have a black hole forming from the collapse of a star, then there it is. It sits at the origin. So remember that this line on the left is just r equals 0. It's just the origin in a spherical coordinate system. So the edge of the star is here, and it eventually collapses into the singularity. Okay, and what we want to do is we want to understand, in this situation, an actual black hole, what is the state of the quantum fields up here somewhere? Okay, so what we want to show is that there's outgoing Hawking radiation. And that means we go up to this part of the diagram, we wait, we let the black hole collapse, we wait a little bit, so we don't have to worry about transient effects at the collapse. And then we ask, what is the quantum state of the fields around here? So that's what we're interested in. What is the quantum state of the fields around here? Was there a question, Elliot?
No, I was just noticing that if you were to fall into such a black hole, you could see the star inside, but you would still get the singularity.
Yeah, that's right. Yeah. Okay. I should label some more things on here. So this up here is Scri plus. That's future null infinity, where light goes. And if we think of ourselves as living far away from the black hole, which I like to think of myself as living far away from the black hole, then we live like somewhere out here, and we're traveling in the t direction, or sitting still. That's our world. Okay, so we're interested both in the quantum state of the fields in this region here, along the horizon, and we're interested in what somebody far away is going to measure. So we basically have already done all the work. And let me just write down the chain of logic to conclude that we've done all the work. The answer is that there's Hawking radiation at the temperature, inverse temperature 8 pi m that we calculated for Schwarzschild. And the logic goes like this. The equivalence principle, which says that people free falling in general relativity don't see anything, says that a free faller sees nothing special crossing the horizon. I'll call the horizon H. Okay, so if you're someone who's jumping in, you're not going to see anything happen particularly at the horizon. And that means that the state of the quantum fields at this point on the diagram is exactly the same state of the quantum fields we had at that same spot on the eternal Schwarzschild diagram. It means this is like a Rindler horizon or the eternal black hole. So if I draw another picture on here of the eternal black hole, then what I'm saying is that the quantum state of the fields in this region here has to be the same as the quantum state of the fields in this region here. Yeah.
Okay, maybe I am confused about something, because it looks like the observer outside of the black hole is always going to be able to see the star, because there are always like light rays coming at 45 degrees from the star before it passed through the horizon to the observer, and so it's never actually going to look black.
Yeah, that's true. That's sort of true. I mean, that's always a property of black holes, that somebody who's outside never really sees the star cross its own event horizon.
Yeah.
But what'll happen is that the light coming like from here will be so far redshifted that it'll be completely undetectable. So what you actually see when you look at a black hole is a black hole. Even though you are looking back at the surface of the star, you can't see it because it's been redshifted. Basically, it's exponentially redshifted in time. So it'll very quickly just look completely black. Okay, so if it's the same as that piece of the diagram, then we're finished. It means that rho in the outside region, which is this region outside the black hole, is approximately thermal, e to the minus beta h, where beta is what we calculated last time, 8 pi m. And that's Hawking radiation.
That part of the diagram looks the same as the diagram in the other case.
Sorry?
Could you repeat the argument?
Well, the quantum state of the fields here is the same as the quantum state of the fields here, which we said is thermal. So what that tells us is that this region here is thermally populated.
How do we know it's the same state?
Because it's the state in which the infalling observer sees no particles. There's only one state like that. That defines the state. And in both cases, we know the infalling observer sees no particles. So that gives us a state. And so that means that according to the ordinary Hamiltonian of somebody who stays outside, it's thermally populated.
Isn't a state like a global thing, though?
Yes. Now I'm having to, well, yeah, the formula for the density matrix rho A that I was writing, that was a global thing. But the density matrix involves modes which are localized somewhere in space or in space-time. So it makes sense to say that the density matrix here is approximately the same density matrix that we had here. That makes sense.
So if I draw a Cauchy slice passing through that region, so where does your argument hold?
You mean where does?
Yeah, I mean a state is defined on some Cauchy slice, right? So if I take some Cauchy slice passing through that region, through spatial infinity set.
Well, a state is defined. States can be defined on a piece of a Cauchy slice. Of course, we can talk about the reduced state.
Oh, reduced. Oh,
And I'm saying it holds on this. It holds on this piece here. So if we take, well, sorry, I should put it outside because we're talking about rho A. Okay, so the state here, obviously it can't exactly be rho A because it agrees with the state here, which is not all of A.
yeah.
But the restriction of rho A to this region agrees with the restriction of this quantum state to this region.
Is that an approximate statement?
Yes, that's an approximate statement. Although, well, it's an approximate statement, but it becomes exact as you go closer and closer to the horizon. Because as you go close to the horizon, you need the quantum fields in this little tiny region to really be in the vacuum state of the person who's infalling. And that requires this infinite amount of entanglement across the horizon that we've discussed. So this statement is really exact in the limit that you go very close to the horizon. And the reason that's good enough is because if we Hawking radiation is a very slow process. Okay, so it's, my picture is getting a little much here. Let me draw a new one. Okay, so Hawking radiation comes from here. And we have to be able to, we live out here somewhere, and we have to be able to detect the Hawking radiation. So of course this is not coming from inside, it's coming from outside the black hole. But this picture is very misleading. It's all really coming from extremely close to the horizon. It's all really coming like from very close, because we have to wait a long time before we can see it. So it's really only the quantum state of the fields in this little tiny piece straddling the horizon there that is going to have any influence on Hawking radiation. In that limit, this is exact, so we really get the right answer from this. A few comments. This argument applies only to the outgoing modes. In particular, if I go back to the picture we had at the beginning, the Hartle-Hawking state that we discussed last time is a state of a radiating black hole that's in thermal equilibrium with some incoming radiation. I'm going to try really hard not to draw on the blackboard with this. Okay, so there's incoming radiation, and there's the Hawking radiation. But the argument we just made was all up here, and you don't see ingoing radiation up there, so that is not part of the argument. So it's the outgoing modes that are thermal in the black hole. So therefore, the physical state of the quantum field theory following black hole collapse is what I defined last time as the Unruh state. The Unruh state, recall, is the state that is thermal for the outgoing modes and empty for the ingoing modes. That makes sense. I mean, obviously, by forming a black hole, we don't suddenly create a bunch of radiation at infinity falling into that black hole also. So it had to work out that way. Now, as I said last time, the Unruh state in the eternal black is singular on the past horizon of the eternal black hole. But that's fine, because the physical black hole has no past horizon. That's just not part of the space-time. So it's perfectly okay for this to be in an Unruh state.
So again, this is kind of an approximate statement, right? Because the Unruh state was defined in a different space-time than we have now. So it was the spot defined in the space-time for the eternal black hole.
Yeah, this is approximate exactly this. I'm just restating what we were saying there. It's approximate in the same sense, but exact also in the same sense.
Okay.
Comment number 2, I'll just write it, but I said it. Real black holes radiate at temperature 1/8 pi m. Now, we've done this calculation. Well, let me write a formula first. So the emission rate for a mode of wave number k is the blackbody emission rate, 1/e to the beta omega k minus 1, times a correction factor, and I'll write as sigma abs of k. Okay, so what's going on here is what some people were alluding to. So this here is the blackbody formula. And this is the absorption cross-section of a mode of this wave number scattered against the black hole. The reason for this is that I was giving a near horizon, I gave you a near horizon argument. Here's a good picture. Okay, so it's perfectly black body if we go in this region here, but these modes are still near the black hole, and they need to escape out to infinity. So so that means that they have to do a one-dimensional quantum mechanics scattering from barrier problem, like you've done in your quantum classes. Okay, so you have to solve this scattering from the barrier problem, and there's a transmission probability for escaping, which is equal to the absorption probability. So it's usually written as absorption, but it's equally the transmission probability. Okay, so this is called the Graybody factor. Let's see. One other comment is that when we discussed under-radiation, I gave you this path integral argument, but in Carroll, in the appendix in Carroll, you read about the free quantum field argument, like the one with A's and A daggers in it, and I briefly sketched it here on the board. You could do the same thing for black holes that form from collapse. Okay, so you can find the quantum state in terms of the A's and A daggers of the quantum field in the collapsing black hole geometry. That's exactly what Hawking did in his original paper. So if you feel like I skipped some steps by making this, by like jumping to the eternal black hole and arguing it was the same near the horizon, okay, all that stuff you could do in great detail using the A's and A daggers in the collapsing black hole geometry itself. That's what Hawking did. Is there a question? Yeah.
That thing you said about the state being similar just outside the horizon, why doesn't that hold a little inside the horizon?
Oh, it does, as long as we're in this whole circle. Yeah, it holds here. But when I was talking about rho A, I was talking just about this. But you're right. Everything inside the green circle agrees with everything inside the green circle.
I see. So when you said here that it applies only to outgoing modes, that's just because there are no incoming modes in this challenge?
Yeah, that's right. The ingoing modes, meaning the radiation that's falling into the black hole, is kind of down here, and you just don't see it in this argument.
Okay.
Yeah.
So usually, like, how much of a mixed state you get is related to how much information you trace out in quantum mechanics. And in the Ringler case, the region A and the region B had the same size, kind of, and we traced all of B because we were accelerated, so we get a fully thermal thing. But here, I understand that the equivalence principle does this, but what you're tracing is the inside of the black hole, which is smaller than the rest of the universe, so why is it purely thermal?
Great. Okay, this will be fun. Okay, so this is a good question, and we'll probably come back and say more about this, but let's see. Let me draw a slice. Okay, so this has a name. Well, let me not talk about the name. Okay, so out is this region here, and in is this region here, and the quantum fields on the union on the full slice. The quantum field theory is in a pure state by assumption. Okay. Now, you're right that so it's by tracing out in that we get some state on out with some outgoing Hawking radiation in it. Now, it's true that the inside of a black hole is it's sort of true that it's small, but it's actually big in a sense. Okay, so if I sort of draw a movie of this, what this is doing, then when a black hole first forms, it's sort of it's sort of a tube like this with the star down at the bottom of the tube. That what I'm doing is I'm drawing the spatial geometry on this first slice here. But as we go further in time, you may have seen discussions, like in a GR course, you may have seen the discussion of the Einstein-Rosen bridge and how it kind of stretches and squeezes as you go in time. And the same thing is true here. So what happens as we go to a later time is that this gets longer and skinnier. And the star is down here somewhere.
Is this a constant T slice?
No, it's not a constant T slice, because T only covers the outside.
Right.
It's the slice that I've drawn.
So what's special about that particular slice?
Nothing. Nothing. You can draw this picture many different ways. Yeah. And as we go later, it just becomes sort of long and very skinny. Okay, so the black hole singularity. So what I'm drawing here is I'm drawing the r direction, or the space direction going this way. Now there's also the sphere directions. So these pictures are telling you how big the sphere direction is as a function of the r direction. That's what these pictures are telling you. And so the sphere is shrinking, and the black hole singularity is when this sphere shrinks to 0. Okay, so you should think of the black hole interior as being this region that's stretching out and shrinking until it shrinks just to 0 size, and that's the singularity. But as far as this question about what you're tracing out and everything, what's happening is that, let's say the horizon is like here in this picture. So Hawking radiation is creating some think of it as think of these modes across the horizon being entangled with each other. And after some time goes by, this one is escaping, and this one is sort of frozen where it is, but it's being stretched, so it's there. And at that point, you create a new one. And then you keep pair creating and stretching, so that at late times you have these interior partners of the Hawking radiation filling up the black hole interior, and a bunch of Hawking radiation that came out, and all this Hawking radiation is entangled with the matter that's on the inside of the black hole. So the inside of the black hole is actually really large in the sense that it grows in the length direction. Yeah.
How soon does this process start? Like astrophysical collapse? Like, is it like a scrambling time later, or is it what? So the star goes past its event horizon. I don't think Hawking radiation starts immediately, does it? Or is there like some?
It's very fast. I'm not sure about the log factors, like in the scrambling time that you're referring to, but it's gonna go into thermal equilibrium extremely fast. Any like leftover excitations or whatever from the collapsing star will go away exponentially. Will be exponentially suppressed. And really, I think in a couple of light crossing times of the black hole, it will just be completely black and radiating at this temperature.
Okay, so it's not like the scrambling time. Because the scrambling time, it's like we throw something into an already established black hole and then wait. But this is.
Yeah, I don't think the scrambling time is relevant to the onset of Hawking radiation. It's really just the thermalization time, which is a faster time scale. Okay. Yeah.
So in this argument, it looks like as the tube is getting narrower, there's more and more Hawking modes inside, right?
Yeah, that's sort of true, because these are coming out, but they're entangled with stuff that's inside.
But the entropy of the black hole is still finite, right?
Yeah, this is the information paradox that you're hinting at.
Oh.
Yeah, that's right. That's right. I was going to say it differently, but the entropy of these guys inside the black hole is getting extremely large, and we thought the entropy of a black hole was set by its area. So what's going on with this? Well, that's a part of the information paradox, and we're going to come back to that.
But is there an infinite number of those modes that are entangled, or is it just a very large number?
Well, it's not an infinite number, but the problem is that the entropy of the black hole is this area, which is going to 0. So you're getting all this entropy here, which is of order the initial entropy of the black hole, but now the area of the black hole is shrinking to 0 because it's radiating,
Okay.
and so it's not enough to accommodate all this entropy you have here.
Right.
Well, the entropy is finite. The entropy is finite. You're right that I can't literally. These mode pictures are sort of imprecise, but the entropy is finite. Now I'm going to draw the semiclassical headrest diagram, which is the one I accidentally drew before. Okay, this is more what an evaporating black hole spacetime looks like. So let me explain some things here. Maybe I won't draw the star. Well, let's draw it. Okay. Here's a star. This is just r equals 0, and this line on the left is just the origin in spherical coordinates. There's nothing special about it. It's just the middle. So the black hole forms. It Hawking radiates. The Hawking radiation comes from this region outside, but very close to the event horizon of the black hole. What I mean by semi-classical is that we're just going to think of the quantum fields as being a small effect on top of the classical geometry. Now, it doesn't have to be small in total. It just has to be small. It just has to be slow. Okay, so Hawking radiation is slow, and the approximations that we made in this discussion are reliable as long as the evaporation process is slow. But it can evaporate a lot, and the approximations are still valid. Okay, so it really just evaporates the way you think, which is that it has a temperature, and it evaporates. It decreases in mass according to the amount of energy that it evaporated. As it decreases in mass, the temperature changes a little bit because of the 8 pi m. A short-shell black hole actually gets hotter as it evaporates. And so the black hole is getting smaller as you go up this picture until you get to this point here, where the black hole just shrinks to 0 size. And at that point, the black hole is gone. You just have the radiation. So you have a bunch of radiation here that came out, but no black hole. And then this line here is just r equals 0 again in spherical coordinates. Again, nothing special about that line. It's just the middle of the space-time. So you start out having this evaporating black hole. It shrinks to 0, and now it's gone. And at late times, you just have Minkowski space with some radiation in it. outgoing radiation. Yeah.
At what point do our approximations on like the quantum states break down in terms of the length scale when it shrinks to zero?
Well, that's also the.
Is there some sort of like string scale going
Um,
on here, or energy scale? Because obviously this temperature goes as 1/8 pi m. Is it just going to keep increasing?
The answer is that we don't really know. We don't know for sure what the next effects are that come in to correct this. But you're also sort of asking about the information paradox. I mean, the information paradox. Let me just say it. Is the fact that this state here. So there's that sigma that I drew there. That's the whole universe. That sigma. The black hole is gone. Okay, that sigma is the entire universe at late times, and the density matrix on that slice is a thermal density matrix. Well, only for the outgoing stuff, but it's certainly a mixed density matrix, and you started out with a pure state.
I think another way of what I was asking is, in what regime near the horizon, if we were to go in and try and talk about our state near the horizon, at what point does the picture you drew over there?
You mean at what point as we go this way?
Yeah, like what's the, when
Well,
we do
cer-
semi-classical physics outside the event horizon, how late in its time and how late in its lifetime and how early in its lifetime are we talking?
Yeah, the standard answer, where by standard answer I mean like, we all know it's wrong, but the answer is that all these approximations are good as long as curvatures are small. You know, that's how like quantum field theory normally works. That's how effective field theory normally works, is that you're allowed to use it until the effective field theory breaks down, and you can see when it breaks down by looking at when the higher curvature or higher derivative corrections than the Lagrangians start to become important, or quantum corrections. And if you apply that logic here, what you'll find is that it's really only when you get within a Planck distance of like when the black hole is Planck sized, that's when it breaks down. So naively, everything I said is completely correct up until when the black hole hits the Planck scale. Or if you posit some scale of new physics below the Planck scale, like a string scale, then it's when the black hole hits the string scale. But we know we strongly suspect that that's wrong because of the information paradox. Okay, so we don't like that it's evolved into a mixed state because quantum mechanics is not supposed to do that. So we strongly suspect that something I've said here is not true.
But
Okay.
can you just say that this breaks down once the black hole gets to be the Planck scale, and the line that you drew as amperes gotten that small?
Yeah, let me postpone the answer to that, but there's not enough energy left here to like suddenly spit out all the information.
Okay.
I'm going to talk about like the various ways you can attempt to solve the information paradox more systematically later. For now, I just wanted to kind of lay it out there and say that this is where the problem came from. This is roughly how Hawking stated it in 1976 or so, and is roughly how it still stands today. That we know a lot more, and we have a lot of ideas about exactly which of the things I said might be the wrong one, and we're going to come to that later in the course. Yeah.
I'm confused about the evaporation part. I understand that due to conservation of energy, have radiation, something has to give that energy. But if you look at the equations and how we solve everything, you have a background metric, which by definition is background, so it shouldn't change. And on top of that, you do some quantum mechanics and you find a thermal density matrix. So if anything, I would think that violates conservation of energy. But I wouldn't change the background metric because it was background.
So in what I've written here is the Einstein equation. G mu nu is 8 pi T mu nu. In semiclassical gravity, which means we treat quantum effects as small, but we incorporate their effect on, they do carry energy. You know, the quantum corrections do have energy, and they have a stress tensor and everything. So in semiclassical gravity, the Einstein equations, you just plug in an expectation value in the right-hand side of the Einstein equations. The reason it works out is because if you look at the stress tensor of the Hawking radiation, it's non-zero. And in fact, the stress tensor of Hawking radiation has a negative flux across the horizon. So that's why. So it's able to extract that energy, and it all fits with the Einstein equations and everything.
You mean like it's pulling energy out of the horizon, when you say negative flux into the horizon?
Yeah, it has a. There's a negative energy flux. If you calculate this stress tensor along the horizon, you'll find a negative energy flux, which is a little weird. I'll come back to that too. Negative energy should have you a little bit worried. Yeah.
So we were just comparing the modes close to the horizon when we said that the state should be the Unruh state. So maybe it's actually a pure state, and it's just like, since we traced out everything that wasn't close to the horizon, it looks like a thermal state. Maybe it's just a pure state that looks like a thermal state close to the horizon or something.
No, that doesn't work. I mean, I agree that I haven't really addressed that potential loophole, but it's not going to work. What you would need for that to work is to somehow entangle the stuff that's very far away with what's happening near the black hole, and there's just no way for that to happen. So, yeah.
How does this relate to the infinite stress energy at horizon part? Is that
Good. Say somebody came along and said, I don't believe you, you picked the wrong quantum state. I have this other quantum state which doesn't have any particles coming out. And you could take you could try to calculate T mu nu in that other quantum state with no particles coming out. And you wouldn't see any flux coming out of the horizon, but it would be infinite when you got to the horizon. Okay, so that state is bad because it's singular on the horizon, and you'll see infinities when you get to the horizon. The actual state, the state that we're talking about that does Hawking radiate, has a finite and smooth, but slightly negative stress tensor at the horizon. Yeah.
Can I say that the Hawking radiation is coming from the assumption that the horizon is smooth?
Yes.
Something
Yeah.
with the horizon what?
Smooth. Yeah, the Hawking radiation is fundamentally relying on the equivalence principle, and by equivalence principle, I mean the smoothness of the horizon. You know, the equivalence principle is just a fancy way of saying that if you zoom in far enough, every manifold looks flat. Okay, so if you zoom in far enough, this just looks like Minkowski space. We think we're in a reliable approximation. We think we can zoom in and just treat this as special relativity near the horizon. That's what I mean by equivalence principle. And that's the same as saying that the horizon is smooth. You know, if you have a theory of quantum gravity where, like, right when this crosses the event horizon, like an elephant jumps out and whacks you with a club if you try to jump into the black hole, that's not smooth at the horizon, and I see no reason that you would have to have Hawking radiation in that somewhat strange theory of yours. That's called the firewall.
This
Yeah.
T mu nu that's finite at the horizon, you're saying it doesn't have to be regularized at some points of fraction or something?
Oh, it has to be regulated, but these are all renormalized. These are all renormalized.
So the thing that's infinite after renormalization, or the other state,
Yeah.
that has infinities even after this is done.
That's right.
So that's, okay.
Yeah. Yeah.
If you look at the same evaporation argument for the classical diagram, what happens at the vortex that R equals 0 hits?
Sorry, what's the question? It's a, you mean,
Like here when...
The green dot.
this green dot?
Yeah, for that.
Up there?
diagram.
Well, there's no green dot on that picture. The green dot is when the horizon of the black hole shrinks to 0 size. And if the black hole is, if we're not back reacting, okay, so this procedure I described where we plug that one loop stress tensor back in and plug it in the Einstein equation, that's back reaction of Hawking radiation on the geometry. If we don't include back reaction, then the black hole doesn't shrink, and it just that situation never occurs. Okay, this is fun and important, so I can keep answering questions, but we can also continue. Anything else? We're gonna I mean, we are gonna come back to this like more systematically a little bit later. Yeah.
What is the current status on people's opinions of the equivalence principle in these sort of scenarios? Because there's a lot of talk nowadays about having large string fluctuations up to the horizon. And what is there any sort of consensus on the equivalence principle nowadays, or is it just what you were saying earlier?
I'll give the short answer now, and I'll try to give the more systematic answer later. But that's one of the possibilities that people discuss, is that horizons just are not what we think. That like this whole piece of the diagram is just like something crazy. It could be some effect of string theory. It could be just something we don't understand in quantum gravity, or just somehow we have to get rid of the whole thing. That would definitely violate the equivalence principle, but it's one of the 3 or so possibilities that people still take seriously.
So you'd say at this time people want to avoid arguments, if they can, that would drop the equivalence principle?
That would drop it?
Yeah.
Well, I do. I want to avoid arguments that drop the equivalence principle, but there are still people seriously working on things like this, which do drop the equivalence principle.
So, observationally, like maybe in the future, far future, how would you check whether the horizon is smooth or not?
Well, you need a volunteer.
Brave soul.
That's a very difficult question. Exactly, because you know, as I sort of discussed like in the first lecture, we don't exactly know what the allowed questions are in quantum gravity. You have to include quantum effects here, and you have to be careful about that. And local observables are not entirely well defined. You kind of have to shoot things in from infinity and look at things like the S matrix. And there is no S matrix observable. There is no S matrix element. At least naively, there is no S matrix element that tells you whether the horizon was smooth. And that's really part of the trouble, and that's why people still argue about whether it's really smooth or not, because anytime if I try to give you an argument, you could say, well, you use some local observable that might not make sense in quantum gravity, and then I have to accept that. So, yeah.
Can you explain again why, probably it should be obvious, but why it's the equivalence principle that's telling you it has to be smooth? I mean, I understand if you're talking about a short-shielded black hole or whatever, then the equivalence principle tells you can't see anything going to the horizon. But if it was just some like crazy thing that wasn't Schwarzschild, but some other space-time or something on the inside, why would you need the horizon to be smooth?
You wouldn't. You wouldn't. So like, what if the star never collapsed?
Right, yeah.
So like the Penrose diagram of a star looks like this. And if we're a astronomer who stays outside the black hole, we could try to distinguish between these two things. And sometimes it might be difficult, like if this star is, well, if it's not a bright star, it's a very dim star, then what's the difference? Well, stars don't have a smooth horizon, and they don't Hawking radiate. That's why stars don't Hawking radiate, in a sense. When I say equivalence principle, I guess I'm really using that almost synonymously with smooth, where by smooth I mean locally Minkowski. Okay, so I'm really using the words equivalence principle just to say that this is locally Minkowski space and that it's empty in particular. Okay, so it's not Minkowski space with like a star surface hiding in it. It's just empty Minkowski space.
But like if there were like a star surface right there or something, then
it wouldn't be smooth in that sense. Well, I wouldn't call that smooth. That would be like there's some stuff there, and it wouldn't Hawking radiate, or wouldn't need to Hawking radiate. Like just like this situation.
right. Okay. Is that a possibility?
I would say that fits into the ones into the like idea that maybe black holes just don't have interiors. Maybe there's something else takes over. You know, maybe black hole interiors don't exist. Black holes don't exist. There's just something that's kind of star-like instead. That's a possibility.
Yeah.
It's it's I would say experimentally disfavored. I mean, you have to work hard to get it to work. It's not like you can just put a star there. Experimentally, you can measure whether there's a surface of an actual black hole, because if you hit a surface, even if it's a cold, dark surface, if a bunch of stuff hits it, it will heat up. Okay, so there are strict limits on whether a black hole can have a surface or not, and they can't. Okay, so there's error bars on that, of course, but they can't have a surface. So to get around this, you would have to find some theoretical explanation that, for most intents and purposes, looks like a black hole, but somehow isn't smooth enough for Hawking radiation or something like that. Yeah.
So the event horizon is defined as the boundary of the causal path to future non-infinity.
Yeah.
So you need to know the whole space-time before you can define the event horizon.
Right.
And so people say event horizon would be forming in this room, and we wouldn't know. Doesn't that suggest that it has to be, local physics has to hold, it has to be a smooth thing? Because otherwise, I could be doing an experiment in this room, and I wouldn't know until the space-time is complete whether or not there was an event horizon forming in this room.
Yeah, typically when people try to break the equivalence principle, they try to break it at the apparent horizon.
Okay.
To get exactly for this reason. In this situation, the apparent horizon is essentially on the event horizon, so I didn't distinguish between them. Yeah.
Yeah, so just to understand your answer to my question, you are saying that if the horizon was not smooth, I would not know that by doing measurements on asymptotic observables. Like I need to make local measurements to. Is that?
That's right.
But
That's
how come
right.
if the horizon is not smooth, it is affecting the correlations of modes, right?
Well, yeah, but we get ourselves into a bit of a situation following this logic. Okay, we can detect it from infinity.
Yeah.
By checking by checking quantum mechanics. Okay, we think quantum mechanics is true. This is exactly why the information paradox is hard. Okay, you can make different logical arguments that all sound correct and give different answers. So here's an answer. Here's explanation number one. Effective field theory is good because curvatures are small, quantum effects are small, therefore the horizon is smooth. Here's answer number two. quantum mechanics is unitary, and smooth horizons produce non-unitary dynamics. Therefore, the horizon can't be smooth. Okay, so we get into trouble, and ultimately we need to decide what to throw away or what to modify. Yeah.
If I do the way like Hawking did the calculation, I look at mode level transformation. In which step did I put in a horizon smooth?
Let's see, because you're saying that argument seems to happen outside the horizon.
Yeah.
But I think the answer is that, so Hawking's argument has a bit of a cheat in it, and people, I think, I'm not totally sure of the history, but I think people were worried about this for a long time, and that's why the argument is usually phrased the way that I do it, the way that I did it. So, in Hawking's argument, the problem is that the Hawking radiation is coming from very close to the horizon, like exponentially close. And if you take the modes that are Hawking modes up here, and you track them back to where they were early on, they have to go through when they're here, sort of going through the collapsing shell of matter, they're at Planckian energies, a Planck distance from the horizon. I believe, I think I'm getting that right. Okay, so there's this, or maybe even super Planckian, there's this thing people call the trans-Planckian problem, which is that if you really try to follow the modes as Hawking did, then you're going beyond the regime of validity of your effective theory. You're not really allowed to do that because of the Planck energy scales involved. I think the answer to your question is in there somewhere, that you're assuming something you're assuming what's happening a Planck distance from the horizon, which might as well be on the horizon. The point of describing it the way that I did is that it's more robust. So Hawking originally did the calculation this way, but the point is really that it's an argument you can make at late times without ever invoking this trans-Planckian region. You can just use smoothness up here, and never mention the part where things were at the Planck scale.
So in Hawking's argument, he compared the what modes? Is it on Scry minus and Scry plus? Did he compare those modes?
Yeah, I believe so. Yeah.
So you are saying our argument was rather a near horizon argument?
Well, our argument, so his argument sort of follows the modes like in this way and then back out through the collapsing shell.
Yeah.
And we just made an argument that was all up in that part of the diagram.
Ah.
It's been a while since I read Hawking's paper. I hope I got it right. I think I got it mostly right. I believe that's how he's doing it. Yeah.
Question. So one of the things you suggested was that if you have something inside that takes over, like you said, maybe if there's some stringy thing happening, taking up the whole up to the event horizon, would that give you? So that has to take up over at some point during the black hole evaporation, right? Like once it gets to some size, then that would have to take over. Does that give you any sort of bound on or not bound, but would that tell you that the string scale would need to be something in order for that to be the explanation?
Not in any way that I know of. I mean, the problem is that just putting in a scale, like just saying, oh, there's a string scale, Well, all that buys you is the last instant. That really only shows up the last instant, and so it doesn't help. You need to not only put in a scale, but also put in some exotic new idea about why.
So there needs to never have been an event horizon.
Well, it needs to. It's roughly half. Okay, you can get away with having Hawking radiation for about half the lifetime of the black hole, because then that's just ordinary production of entanglement, no big deal, that's fine. It's really when the black hole starts to disappear that you have a problem. So you can get away with it for roughly half the lifetime, but then something's got to give at that point. Any other questions? Yeah.
Why is there that extra wedge for semi-classical Penrose versus that?
It's really just because the black hole is gone. So on the classical Penrose diagram, the black hole was never gone. It's just there forever. But if the black hole disappears, there has to be some way of drawing a spatial slice that doesn't have a black hole in it. That's a complete spatial slice covering the entire space without having a black hole in it. So that's why it has that extra thing. Yeah.
And then one of the other ideas is that there's a remnant, right? Where the
Yeah.
black hole never really goes away completely.
Yeah.
And then we just have like a little piece there for the black hole.
Yeah, that's one of the possibilities. Okay, since everybody's asking, I might as well. I'll like write them down and be systematic about it. But there are roughly three things that can happen to save the day. One is that you really have to think of this black hole as still existing, even when you think it evaporated away. So like, in other words, at late times, there's really the whole universe that we see, and this black hole is still there. That's called the remnant. Like the black hole just lives on. It may like disconnect from our universe in some way, but the black hole lives on. Is it what?
Is that the same thing as humans when they pass away?
Maybe. That's next semester. So that's one, remnants. The second possibility is structure, I'll call it, at the horizon. That's the other one I've been discussing, where really just event horizons don't exist, they're not smooth. And the third one, which is the one that we'll discuss the most, is, I don't know what to call it. I'm just going to call it e to the minus s. Okay, so there's a problem is non-perturbative effects. Okay, so there's a problem with this picture, which is that it's still a semi-classical diagram, and in quantum gravity you can imagine really crazy things where these pictures just don't make any sense. Like, what if there was a quantum fluctuation? We have a space-time. What if there was a quantum fluctuation that, like, the black hole disappeared by a quantum fluctuation and then reappeared? Or what if this region over here, which seems to be space-like separated from infinity where we live, what if it like came out for a minute and then went back through some sort of quantum process? Now, that's a very subtle thing, and you can't just postulate that. You have to explain what you're talking about. But that could potentially spoil the arguments that we were making in a way that preserves unitarity at infinity, preserves Hawking radiation, but messes with our usual notion of locality. Okay, no, we think the inside of the black hole is causally disconnected from us, and it could be that non-perturbative effects make that not quite true. That it could be that it's not quite disconnected from us, and it's actually somehow related to what we can see out here. So that's well, that's I think the most compelling way out, and we're going to discuss that later.
So
Yeah.
when you said that you want to use non-perturbative effects, so do we know that perturbative effects won't save the day?
Yes, we do. What do I want to say about that now? Yeah, there's a really nice little theorem. I might even prove this theorem now that you mention it a little bit later. But there's a really beautiful theorem which says that, well, our argument relied on having a thermal density matrix in this little circle here. What if that was just not quite right? Like, maybe when you include the back, people have speculated about this for a long time. Like maybe when you include back reaction, the black hole shrinks a little, and that like modifies the Hawking radiation that came out. It's not quite what Hawking said. Maybe there's a tube loop effect that nobody calculated yet. Maybe it only shows up in 27 loops. All stuff like that is going to make small corrections to this Hartle-Hawking density matrix that we had for the fields at the horizon. And there's a very general theorem that says that small corrections to the near horizon physics can't help. They can't help basically at all. So no matter what you do, if it's some small local tweak, you could change the laws of physics a little bit near the horizon, but as long as it's quantum mechanics and everything, it's not gonna help.
By small corrections, you mean corrections which are perturbative in G Newton? Is that what you mean?
Well, it's really just you could say it that way. So corrections which are perturbative in G Newton will not help. But this theorem is just an information theoretic statement that no matter what you do to this density matrix, that will not be enough to transfer the information out to infinity. And to phrase that theorem, you have to use like quantum entanglement inequalities and relative entropy and stuff like that. So we'll probably come to that. Yeah.
So in all three of these proposals, is the end game that you want the state after the black hole has collapsed for the state on the spatial slice to be pure in all three of these?
Well, it depends what you mean by, so in remnants, yes, but you have to imagine including this little thing there.
Right.
Yeah.
And then with the structure,
with structure, there's really just
there's
not
no Hawking radiation. Right?
Yeah, well, there's either no Hawking radiation or there might be radiation, but it would just be like a star. Like if you make a star and it burns, no big deal. It might just be like that.
Okay.
If you had structure.
And with the non-perturbative effects, what do you get at the end?
With the non-perturbative effects, the goal is to get a pure state of the radiation on this thing with no remnant.
Okay. Is there an easy way to see why that might be possible? Like with the remnants, it's like, okay, you include this like extra little bit and it's pure.
Yes, but let me postpone it. I mean, we have to talk a bit more about. Well, okay, since we're doing all the answers. Okay, so the answer is, it's easy to see that it could work. It's not easy to see that it does work. It's easy to see that it could work, because when we said that this density matrix was thermal, what did we really mean by thermal? Well, we really meant that it's a thermal density matrix, possibly plus a bunch of little corrections with e to the minus s's. And it's very easy to see that you can take a thermal density matrix, and if you allow me to just stick e to the minus, this is just some big matrix. If you allow me to stick e to the minus s corrections anywhere I please, I can turn that into a pure state. Now, you have to hope for some miracle for that to actually happen from the physics. But it's not, if you just sort of count, are these effects big enough to make this state into a pure state, the answer is yes. All right, let's stop there. Move on to another topic next week.